Hello. In this video, we're going to talk about stability of a system and how we evaluate the stability of a system. So basically, evaluating a stability of a system. There are different types of systems. We have seen that the stability of a system is related to its frequency response and the location of the system poles. In essence, a single pole system, meaning a system with a single pole, can produce a maximum phase shift of 90 degrees. And because we have seen that the problem of instability is related to negative feedback becoming positive feedback, and that occurs when our phase shift reaches 180 degrees, we can conclude that single pole systems are always stable, or the term of art will be they're unconditionally stable. And that's because their phase shift never exceeds 90 degrees. So if we have a single pole system, evaluating stability is very easy. It's just always stable. Maximum phase shift for a single pole system is 90 degrees. That can go in either direction, plus or minus, depending on whether you have a high pass or low pass filter type of response. But they are called unconditionally stable. For multiple pole systems, it's a different story. Because once you have two poles or more, then you have a maximum phase shift that can be equal to or exceed 180 degrees, and therefore you have the potential or the risk for instability, which leads to oscillation. So maximum phase shift in this case is greater than or equal to 180 degrees, and therefore risk of becoming unstable. And what I mean by that is that they will oscillate. If you remember from your circuits 3, the stability of a system is related to the location of those poles. If you wanted to think of it in the S-plane, so if I'm representing again my S-plane, and this is my real part, that's my real axis, my imaginary axis, you should have seen that generally any poles that are located to the left side of that j omega or imaginary axis are going to cause, are going to decay, basically an exponential decay. And so they will look something like this, the type of response, right? How fast they decay is related to how far they are from the origin. In the case of poles that are located to the right of that imaginary axis, what we have, instead of an exponential decay, is an exponential increase. When we had complex conjugates that were exactly on the imaginary axis, what we had was a sustained oscillation. And then if we had complex conjugates to the left-hand side of the imaginary axis, we basically had a decaying oscillation. The rate of decay determined by the real part and the frequency of oscillation determined by the imaginary part of those poles, right? And on the right-hand side, the same thing, except we will have an increase in oscillation, where the rate, oops, that one looks like it decreases again. That was not the intent. And the rate of increase is related again to the real part of that pole. And so basically, graphically speaking, or graphically looking at it, we're interested in systems that will have their poles to the left-hand side of that j omega axis. Those will be what we consider stable systems. And the reason for that is because they have a decaying response for the transfer function. And even if they have an oscillation, it is a decaying oscillation, so it's going to decay in time. Whereas if you have poles right on the j omega axis or to the right-hand side of that j omega axis, what you have is a sustained oscillation, or the worst case scenario, an increasing oscillation. Okay, so those could be the unstable systems. How do we relate that to our body plot, that is the graphical tool that we typically use to represent and to study the frequency response of our systems? And we can do that using the Nyqvist Stability Criterion. And the Nyquist Stability Criterion basically tells us that the system is stable. System is stable if it meets the following condition: that at the frequency at which the loop gain magnitude is unity, the phase shift is less than 180 degrees. Okay, so, and basically that is because by the time you reach a phase shift of 180 degrees, your your gain loop magnitude is less than 1, less than unity. And so that really implies, even if you had an oscillation, it will be a decaying oscillation. You're multiplying times something as you go through your feedback loop, times something that is smaller than 1. And so it just means that even if it adds, it's going to be smaller and trending to 0. Okay, so let's go ahead and write a system is stable if at the frequency at which the loop gain reaches unity, the loop gain magnitude, I should say, unity, that's to say the magnitude of the closed loop gain is equal to 1 or 0 dBs, the phase shift is less than 180 degrees. So notice that it's basically based on a relationship between the gain of the magnitude, the gain or magnitude response, and the phase response. So a relationship between the two of a system, the loop gain magnitude and the phase shift. Loop gain magnitude being equal to 1, phase shift being less than 180 degrees. If that condition is met, then we can be certain that the system is stable, or almost certain. We're going to see how there is a little caveat to that. And again, why is this? And we said basically because if by the time you reach your phase shift of 180 degrees, your magnitude of your loop gain is less than unity, then it implies a decaying type of oscillation, okay? Not a sustained oscillation. Now, why did I say that, this almost defines an unstable system? Well, notice that at the verge of instability, we have the following condition. We have that AF equals 1 at exactly the same frequency when the phase shift equals 180 degrees. That will be the verge of instability. Mathematically speaking, the system will still be stable. Practically speaking, that's bad news. And the reason for that is because any disturbance in the system can bring it out of those conditions, can make it not meet the condition for stability, the Nyquist criterion, and therefore any disturbance can bring about some oscillation in the system. And this typically, for a marginally stable system, they're typically going to be intermittent oscillations, which are going to be even more difficult to troubleshoot. So basically, perhaps we want to put a note here. There's instability. Not good condition in practice, because disturbances may cause intermittent oscillations. And so practically speaking, we will still define a marginally stable system as an unstable system. But technically speaking, this could be what we call a marginally stable system. All right. And so the idea here is when we are designing, we want to leave ourselves some room. We don't want to be on the verge of stability or on the verge of instability. We want to allow ourselves some room, so to make sure that we are well within the stability area of the amplifier. And the way we measure the degree of stability of a system is by two factors referred to as the gain margin and the phase margin. And as the name indicates, they tell us how much margin I have left between the marginal stability and my actual system. So basically, two factors determine degree of stability. Of a system, and those are gain margin. We are typically going to be referring to it just by its initials, GM. And that's basically the difference between the unity gain frequency and the gain at which the phase shift is 180 degrees. So difference between frequency at which phase shift is 180 degrees. Now this is kind of poorly written because this might sort of imply that that the gain margin is measured in degrees. It's actually measured in decibels. So perhaps I will write as difference in gain between the unity gain frequency, meaning the gain value at that point, and the gain value at the frequency where the phase shift is 180 degrees. So perhaps I will rewrite this as difference in gain value between unity gain frequency and frequency at which a phase shift is 180 degrees. If I were to represent this graphically, which is easier to see, I can go ahead and represent, this will be my closed loop gain in dBs versus frequency, and this will be my magnitude response for my system. And I put it in blue, and I have something that looks like this. And it's kind of smooth, but you can see that there are approximately 2 poles here, one here, because the rate of decay starts at a rate of what should be around 20 dBs per decade if we have a single pole at that point. And then if here there was another pole, then the rate of decrease of my gain will be larger, minus 40 dBs per decade if that's just a single pole at that location. And then I will have my phase response. Let's imagine for simplicity a 2-pole system. And so I'm going to only represent from 0 degrees to negative 180 degrees. And it will go right at the first pole. It's going to hit minus 45 degrees. So it's going to go from 0 to negative 90 around the first pole, and then from negative 90 minus 135 at the second pole, and eventually 180. And let's imagine that it stays there until the next pole comes along. All right. Now, how will I measure my gain margin? Well, first I want to indicate in my graph the location at which my gain has reached 0 dBs, or the unity gain. And I could represent that here, for example. Let's imagine this is my A, F equals 0 dBs, or 1 in linear scale. That will be that location over there. And then another point of interest will be the point at which my phase shift reaches 180 degrees. And so basically, and I guess the way I drew it, it just never did. So to make the graph a little bit more interesting and more accurate, I'm going to go ahead and modify this slightly so that it does reach the 180 degrees. For example. And so I have this other point out here where I have reached 180 degrees. And that corresponds to a certain gain. So in essence, my gain margin is going to be the difference in gain value between the point at which my gain has reached 0 dBs, or a value of 1, and the gain at which my phase shift is 180 degrees. This is my gain margin right here. And mathematically it is defined so that it is a positive quantity, and so it's going to be mathematically going to work out so that obviously if I have a gain margin where I reach a gain of 1 before I have a phase shift of 180 degrees, that works out to be a positive gain margin, which is a good thing. So that will be my gain margin. The larger my gain margin, the farther away I am from an unstable system. So, and then the other descriptor, or the other factor that determines the degree of stability, is the phase margin, which I'm going to represent with the capitals PM for phase margin. And that's basically the difference in phase shift between the unity gain frequency point and 180 degrees. Phase shift between the unity gain frequency and 180 degrees. And so in this case, I have, it's the same 2 points if you realize that you're measuring for the gain margin, so they are related. But now I'm measuring those 2 points in my phase plot. Basically, the difference between the point at which my phase shift, at which the frequency for which I have unity gain, and the frequency for which my phase shift is 180 degrees. This amount of phase shift is what's termed the phase margin of the system. And I always want to get to unity gain before I reach the 180 degrees for the system to be stable. And so this will be a positive gain margin because I have I'm hitting my 0 dB point in terms of gain before I am hitting the 180 degrees. Okay. Things important to note is that phase margin and gain margin, they are related. And so basically if one margin passes the stability test, the other margin will pass the stability test. So that's something important to note. Note, if one margin passes a stability test, so will the other. And then since we want to avoid marginally stable systems, we know that we are going to want a phase margin and a gain margin greater than 0. But how much greater than 0? And so a typical rule of thumb for design, rule of thumb to avoid marginal stability, will be to try to design for a gain margin greater than 10 dBs and or a phase margin greater than 45 degrees. Those are typically standard values, especially for the phase margin. Sometimes you will even see systems that have phase margin of something like 60 degrees and things like that. But this is a pretty good rule of thumb. And that's about it. We will, from now on, try to determine the stability of systems by simply referring to their gain margin and phase margin. The last one point I wanted to perhaps mention is we talked about the single pole systems as being unconditionally stable. That's because they have a single pole, their phase shift never goes beyond 90 degrees, and therefore, by definition, their gain margin and phase margin are going to be infinity. And that's by definition, since we're trying to calculate differences with respect to the point where the phase reaches 180 degrees, which never happens in a single pole system. So for single pole systems, perhaps another note. Single pole systems have gain margin and phase margin equal to infinity. Again, that's by definition. Next, we're going to take a look at how can we modify unstable or marginally stable systems in order to guarantee stability. That's going to be termed frequency compensation. Thank you.